Guess what?
What?
You went to Los Angeles without telling us on Tuesday?
But someone good came, filled in. We get to talk about linking today. Isn't that exciting? What? It is exciting. Exciting to me. And soon you will share my excitement. Okay, here's an example C program, right? No, we have main.c, right, and swap.c, right? Normally these two things are compiled separately. That is to say, we start out and we run gcc on main.c, it does its whole thing, and it spits out a main.o, right? And then we run gcc on swap.c, and it spits out a swap.o, right? And then together it links these things to form our executable, right? So today we're talking about linking, that process of putting these pieces together. Does that make sense? Okay. So static linking is the part of linking that happens at compile time. Okay? It's the bread and butter of linking. Everything's actually statically linked. And so we take main.c and we run it through, the C preprocessor and the C compiler, the assembler. We produce main.o. We do the same thing with swap. LD, the linker, then produces our executable. Ta-da. Why linkers? Well, one can imagine a world without linkers. Right? Where all programs were written in a single file. Right? It's possible. Right? Just one file for all of Microsoft Word, one file for all of Microsoft Windows, one file for all of Linux. But that would be the type of imagination we call a nightmare. Okay? It'd be terrible, right? Being able to write things in separate pieces allows us to reuse parts of them, right? If I have one .c file and I compile it to a .o file and include it in some library, either as a shared object or part of an archive, right? Then several different programs can use that. We're able to share that code. And if there's a bug, we have to fix that bug once in the module, right? And then we can relink and everything else gets that fixed. We don't have to track down every place that piece of code has been cut and pasted. So modularity is really important, right? It lets us factor things out of our code, find complex parts, factor them out, put them somewhere else. So we can read the top-level code and have a really good idea of the algorithm or the process or what it's doing, and then dive down into these other parts when we really care about them. Efficiency, okay? Let's say that we have one massive .c file. Then if we change one line of that file, we've got to compile the whole massive file. We've got to run that thing through the preprocessor, run that thing through the compiler, run that thing through the assembler, right? That's a huge investment of time, especially when we're talking about truly large, complex software. But with a linker, if we have separate modules, right, then we can compile them separately and then just link them together, which is much faster. If you think about, right, all the processes running on a Unix system right now, Unix.Andrew, okay? And you ask yourself, like, how many of those are calling printf somewhere in the code? Or more fundamentally, write somewhere in the code, right? And then you wonder exactly how many copies of write, that function, do I need to have in that system? If I have 300 processes running, do I really need 300 copies of that function in memory that are exactly the same? Right? Not really, right? A lot better if we can share that. Another efficiency is if you have a whole team working on a product. If that product is one file, who's editing it right now? Is it you, or is it you, or is it you, or is it you? Because it's not going to be all of you. Right? It can't be. Because that means when you save, your changes are lost. And then when you save, those changes are lost. Right? By being able to break things down to pieces, we make it much, much easier to develop that software, to maintain that software over time, to build that software, to test it, right? So what do linkers do? Well, one thing linkers do is resolve symbols. In our code, we have all these symbols. In other words, the names of functions and variables. And right now I'm talking about functions, global variables, okay, and static local variables. Okay? Local variables, as you know, are allocated on the stack. So these global symbols, function names, global variable names, static variable names. We talk about them in our programs like x and y and z using their names. These need to be resolved to their addresses, to an actual location in memory. This can't be done until all the separate .o files are organized together in memory. It can't be done by the compiler, because the compiler doesn't know which pieces are ultimately going to be assembled. Okay? So the linker maintains this thing called the symbol table. It's this table that contains the name of the symbol, like printf or scanf or x or y or z. The address of that symbol, wherever it actually is going to be, okay, and the size of the object. Not the type, just the size. All right? And as it goes through, right, it fills these variables into this table, and then when it sees them again, it replaces them with the same address. This provides the address to symbol mapping. Now, when the linker is done, it can throw this away. It's not needed anymore. Or it can leave it in the final package of the executable so that when you're using GDB for debugging, you can find it there. It's what enables GDB to do so-called symbolic debugging, to let you debug things using names rather than addresses. Okay. Relocation. As we merge these separate .o files together, things need to get moved around. Right? Because each .c file was rendered to a .o file completely independently. And now the code sections need to be merged, and the data sections need to be merged. Right? And when that happens, all of those symbol addresses need to get changed. They need to be updated. Okay. So we have three different kinds of object files, modules. .o files are just simple relocatable object files. These are the most basic. You compile your .c to a .o file. What do we mean when we say relocatable? We mean that the linker can move it around. Okay. An executable file, right, which you could actually run after the linker resolves all the symbols. And you now have actually something that can be loaded into memory and run. And then a so-called shared object. In Windows, these are called DLLs. We'll talk about this, but when it comes to linking, there's static linking done at compile time, and then dynamic linking done at runtime. Okay? And the dynamic linking process allows us to link in code while our program is actually executing. What happens is the static linker links in a small stub and then calls the symbol resolved, because there's this stub code. And then at runtime, if the function, this dynamically linked function, actually is needed, that stub links it in at runtime. Okay? Provides a late binding. Okay? Static linking is good because you produce one big package. Here's your program, everything in it, right? Here's your executable, boom. It's unfortunate because every copy of the executable has everything linked into it. If we do dynamic linking, late binding, then what happens is we can load this object once on our system and let it be shared by everything at runtime. It has some other advantages, like if the library is updated to fix a bug. We can update the library, and now it's fixed for everybody. Next time a program runs, it loads the new version. Okay? So it saves system resources by letting these things be shared. Okay? It provides some software engineering advantages because we can update things. It provides some distribution advantages because our executable file is smaller, takes less time to transfer over a network, less space to store in a disk. Not really super important. Right? It has some cost, though. If I ship you an executable file and it has a bunch of these dynamically linked things in it, the environment on that system needs to provide those things. If it doesn't, it obviously won't run, right? Okay. You hear a lot about ELF files, the executable and link format, ELF. Okay? This is a format that provides a unified way of describing .o files, executable files, and .so files. These are generally referred to as ELF binaries. Why ELF binaries? They're binaries, they're not text files. Okay? And they're stored in this ELF format. And the ELF format just provides a way of structuring them. So this section, this is one section of the file, this is another section of the file, this is another section of the file. That way the loader knows how to load something, right? We have a standard, so when our compilers dump out an executable, or our compile toolchain dumps out an executable, it's in the same format that a loader can load it, right? It looks sort of like this. Okay. We have an ELF header, meaning a header for the whole file. And then we have our sections, right? The text area. And we know what the text area is, right? That is the code. Okay? The read-only data section. All right? That has the constants. The data section has the initialized variables. The BSS section has the uninitialized variables. The things that don't actually exist in the binary file because there's no value to them. But they have to exist when you create the executable. Okay? We have the symbol table. Right? Sometimes we throw that away, sometimes we keep it for debugging. That's the mapping between the symbol name and the address. Also includes its size. Relocation information. The debug section. The debug section provides a mapping from the line name in the source code to the offset in the binary. That way, when you reverse it, you can disassemble the binary and get the assembly. So you can look at a line of source code and say it corresponds to this chunk of assembly. And that's how GDB is able to show you your source code when you type where or list, and show you the assembly associated with that. Okay? So when we talk about global variables and local variables and static variables, we're talking about those generally from the perspective of a programmer. Today, when I talk about globals and externals and locals, I'm talking about them from the perspective of the linker. So the names are going to mean something slightly different than they otherwise do. Okay? A global symbol is a symbol that is visible to all of the objects. Okay? A global symbol is a symbol visible to all of the objects. Please. I thought you were making a donation. I was looking forward to my new MacBook. A local symbol is a symbol that can only be used within an object. And an external symbol is one that's being used within an object but isn't present there. It needs to be resolved by linking. Does that make sense? So global symbols are mostly with things you'd expect. Okay? They're most of your functions and your global variables. Your local symbols are your static global variables. Okay? Local variables are not visible to the linker. They don't exist at compile time. They exist at runtime. So when we talk about a local now, we're talking about a local variable in the sense that the variable is local to a particular .o file. It can't be used by, the linker can't associate it with a variable somewhere else. Okay? So these are going to be our static global variables and our static functions. External symbols are global variables that can be used in other places. I'm sorry, global symbols are global variables that can be used in other places. External symbols are when we're using variables that are not present in a file but are present somewhere else. So you can imagine I have a file called globals.c, and I declare all of my global variables there. Okay? Those are global symbols. You can imagine I have some other file, main.c, mathlib.c, whatever it is, that relies upon some of those global variables. The uses of those variables in that other file are known as external symbols. Does that make sense? Local symbols, if I have a variable that I declare static, so it can only be used within a file. A function I declare static because it's a helper function, and I only want it to be used within that file. Those are going to be my local symbols. Okay? So if we go to look at this, all right, buff is a global variable. Main, right, is a global symbol. Swap is not defined here. It's defined here. That's an external reference. Okay? This is an external reference. It's referring to buff. When the linker was linking this, buff was a global. Now the linker is referencing that, buff is external. Okay? Buff P, 0, global. Buff P1, local. Notice it's static. Okay? Swap, global. Temp, the linker doesn't see it. It is a local variable in the sense that we've traditionally talked about it, meaning it's allocated and freed on the stack at runtime. What some people would call an automatic variable. Okay. And so there you go. When the compiler compiles these things, it compiles main.o and swap.o separately, and then has to merge them all together, taking the data areas and combining them, taking the text areas and combining them. Okay, taking the BSS and combining them. Okay. If we take a look at main, okay, and we look at this, okay, call main plus 12. Okay, and then we see the 12 is r underscore 3, 6 underscore PC32 swap, right? It's this magic -4 value here. That's a relocation entry. That's something that's going to be filled in later on at link time. Okay. Take a look at this, right? We can see a bunch of these. All right. Now, if we take a look at it after relocation, this weird entry goes away, and instead it gets replaced with an actual address. Okay. So we see the address of 8048380, an offset relocation entry of 12, means the pointer is going to be this plus this, or 8048392. The address of the swap function, 80483B0, with a reference pointer of -4. It's going to be 8048392. Yeah, so 80483B0 minus 4 plus 8048392. So the entry is going to be 1A. Boom. Okay. Just another example of that. And another example of that. Okay. When it comes to linking, there are strong and weak symbols, and it's important that we understand the difference. So if a symbol is defined, by default it is strong. And what I mean by that is if a symbol has a value. So int x equals 5. X is being assigned the value 5. It is strong. Int x. We know there's a variable of x, but it doesn't have a value. That's weak. Does that make sense? So a variable as a symbol is strong if it's given a value. It's weak if it's not. An initial value. Okay? Functions by default are strong. Why? I hear whispers. Yes, ma'am. Yeah, that's right. When we're talking about functions commonly, the function has a definition. It's just not a symbol. It's a symbol and the address where the code is. Yeah?
What are prototype functions?
Prototype functions are not seen by the linker. Those are seen by the compiler. And so the prototype function lets the compiler know that a function is coming up. Therefore, it can continue the compilation process. But at link time, it actually needs to resolve that address for that function for real. Does that make sense? Does that answer your question? Okay. Okay. So strong, generally speaking, are procedures that initialize globals. Weak are generally uninitialized things. Okay. Now you can change that. You can hint the compiler and say, "Dear compiler, please give me this thing as make this strong or make this weak." Okay, by using, this is a compiler-specific syntax, but usually it's something like underscore underscore weak underscore underscore as a prefix, as a qualifier, and then it'll take something that otherwise would be strong and make it weak. Now the question is, why do we care, right, whether it's weak or strong? And the answer is we care because when the compiler is presented with two different object files that each have competing definitions, this is going to determine what the compiler does. If the compiler is presented with a weak definition and a strong definition, I'm saying compiler and I mean linker. If the linker is presented with a strong definition and a weak definition, which one is it going to keep? Strong. Okay? If it's presented with two weak definitions, which one's going to keep? What's that? Yeah, it doesn't care. Either one's fine. What if it's presented with two strong definitions? Int x equals 7 in one file, int x equals 9 in another file. What's that? You get a... Oh, sorry, missed it. What's the logical thing for it to do if it has two things that are defined and inconsistent? Yeah?
Wouldn't it just keep the latest value?
Well, one possibility is that it would keep the latest value, but does that sound like that might surprise the programmer? No? In one file you've said x equals 7, in another file you said x equals 9.
Well, if the x equals 9, if the x equals 9 is compiled after that, I would assume that would be the last value stored.
So can you tell me generally, if you're building a big piece of software, can you tell me what order things are being handled in by the linker? It's not something I usually think about, right? And maybe it changes. Maybe somebody edits my make file and moves things around. Yeah.
Would it think of them as two separate variables?
Well, but the question is, would it think of them as two separate variables? Well, it might be nice if it did, but the problem is that it isn't. The identifier is the same. Yeah.
It just gives up.
It gives an error, right?
Yeah.
Yeah. I don't know how this sounds on the microphone. This doesn't have to tell me. That's what it does. Okay, distance into the video can tell me how that came through on the other end. But the answer is yeah, it gives up, right? It throws an error. It says, look, this has been redefined. Okay, so given a strong and a weak, it obviously takes the strong. Given x equals 7 and int x, it's going to stick with the x equals 7. Given int x and int x, okay, there's an x, fine. Okay. So strong, strong and weak, okay. Weak and weak, okay. Strong and strong, bad. Here we see a case of strong because it's initialized. Functions are initialized, right? That's weak because it's not. We've talked through the three rules. Multiple strong symbols not allowed. Given a strong and multiple weak signals, the strong wins. If there are multiple weak signals, any one can win. What happens here? P1's a problem because it's a function and so it's defined. Okay, what happens here? Well, no conflict. They're two different names. There's no conflict with the int because they're both weak. Neither's initialized. Fine. Here, there's no conflict between P1 and P2. They're different. There's no conflict between y and x, but there are two weak x's. So from the compiler's perspective, the linker's perspective, this is perfectly okay. It's a weak variable called x. I'll pick one of them. From the programmer's perspective, who knows more, that really sucks. Because those are clearly not the same thing, and yet the linker has just treated them as if they are. Why? The linker doesn't know the type. The linker just knows the size. Why doesn't the linker know the type? Well, linkers, at least at some level, are language-independent things. Their job is to assemble ELB files. Languages have different senses as to what types are and how they should be handled. Okay. So that's problematic. Over here, more problematic, right? Because now, this one actually has a value, and it's not clear that I want to reinterpret the bits of 7 as double when I come to the other side. Here, x is okay, strong here, weak here. We're okay here, two different names. Yeah?
What is this discussion about overwriting y?
Well, the problem there, you're looking at this, right?
Or the one above you?
So, right. The question is, if this is an int and this is a double, an int and float are the same size. A double is twice as long. So when I have my double here, it's possible, that this double, right, is actually going to be mapped to the address of both x and y. We don't know that because we don't really know where the linker is going to put it. But it's certainly not going to do anything good when it's presented with something like this. It's going to slip right through. Yes?
In that situation, if the linker came across the double first, it'd be okay. But if it came across the int first,
Well, you said the question is, what if it comes across the double first versus what if it comes across the int first? Will either be okay? The answer is, I don't think either is going to be okay, because, well, would the double be okay? Right, so if it allocates more space for the double x, I think you're in a better position of being bad than a worse position of being bad. Right, the problem here is that in this file, I'm treating x as if it's a double and putting values into it the IEEE floating point format, right? Over here, I'm treating x as if it's an int, and if I turn around to interpret one of those values, it's wrong. Which probably means that these two things, even though they're both called x, are just sloppy programmers using global variables that happen upon the same name and are totally unrelated. So really, each of these are corrupting each other's state. And that means this program as a whole is corrupting its state. Does that make sense? Yeah.
Wait, int x equals 7 is strong and double x is weak, right? So shouldn't the strong just get retained and shouldn't y not get overwritten?
So you're talking about this example versus, okay. So down here, right, x is going to be right. X is going to be 4, y is going to be 4, p1 is going to be 4. Okay. Now it comes over here and it says, okay, x is weak, I'm sticking with this one. That doesn't change what happens inside your variable when you say x equals 19.5. Because your program on this side, right, your code still thinks that's a double. Does that make sense? Okay. Okay. So, .c files should contain code. .h files should contain definitions. You should never put, the meat of your code in a .h file. That's very bad form. The linker should do the linking, not the preprocessor. Okay. If you want to declare global variables, you should declare them in a file called globals.c. Oh, this is actually sort of terrible form too. This is not the way I would go about this. The way that you want to declare global variables is put all of your global variables in a file called globals.c. Now all of your globals are in one place. Does that make sense? Now create a file called globals.h that includes externed versions of each of those variables. So if you have int x in your globals.c, you have an extern int x in your globals.h. Does that make sense? Int x equals 7 over here, extern int x over here. Now I include globals.h everywhere. That means that in my C code, I can use those global variables everywhere. Because at compile time, the compiler is going to know about them because they're externed. Then they'll actually get included by the linker when it links globals.c with everything else. Does that make sense? That's the proper way to handle globals. Declare all your globals in a globals.c, extern all those globals in a globals.h, include globals.h everywhere. Then step 4 is for free, where the linker combines everything together for you. This is a convoluted way of dealing with that. Okay. So one thing you want to do is avoid global variables if you can, right? They're very polluting to the global namespace. If you can't avoid global variables, use static, so at least you're only polluting your own namespace, right? If you can't do that, then put all of your globals in a global.c, extern them in a globals.h, let the linker combine them. Don't let the preprocessor combine them. Okay. Okay. So let's say you have a whole bunch of functions, where the functions are somewhat meaty functions. They're not necessarily simple functions, right? We can do a couple of things. You can put them all into a single file. So programmers link this big blob into their code. Kaboom! Okay? Or you can put each of them in a separate source file. So then programmers have to link each individual one separately. It's more efficient, but then programmers have to track down, like, where is this function, right? And sit there and add all the includes, and add all the linking directives. Okay? One solution is an archive file. An archive file basically takes all the .o files and slams them together into a single file. It's called an archive file, and attaches a table of contents before it, where the table of contents tells it where the beginning of each of the original files was. Okay? So you can put things into a .o file. You can get the bits right back out of the .a file. You can put things into a .a file. You can get things back out of the .a file. It keeps them intact. It basically slams the .o objects together to form the archive, keeping a table of contents so it can find them. Make sense? Okay. So here we have a whole bunch of .c files, where each C file is compiled to a .o file. Each of those things is then archived together to form the archive file. And this, again, is a reversible process. You can use the same AR tool, the archiver, to extract an object file from an archive file. Okay. libc.a is the statically linked version of the C library. libm.a is the statically linked version of the math library. Here you can see us using AR-T to view the table of contents. Okay. So most C compilers are single-pass use single-pass linkers, meaning it approaches the first object file, okay, puts it in place, and if there are any dangling symbols, it keeps a table that has them. Then it applies the next one. It tries to resolve the symbols where it can, and then keeps a track of dangling things. And it walks forward and does this. And at the end, if anything's dangling, the link fails. The problem with this might be that if A requires something in B and B requires something in A, it's not going to resolve that. Because the symbols from A that are needed by B will be resolved, but the symbols that need in B that require A are not resolved. To fix that, you'd actually have to list it multiple times at the command line. A, B, A. Okay? So order generally matters here. Some linkers are able to do multiple passes for you, in which case you don't need to do the multiple passes. They're able to do that. But as a general rule, order does matter, right? And you could have to repeat things. Put libraries at the end of the command line is the basic answer there. Okay. So an executable file, right, comes from, an executable image comes from one of the ELF executable files, and basically, right, it just gets mapped out. I have my text area that becomes my process's text area. I have my data area that becomes my process's data area, right? The green stuff is created at runtime. The heap, right, when we call malloc, that grows. When we call functions, the stack grows. If at runtime we dynamically link libraries, handle those shared libraries, those get mapped into the space in between. Static libraries have some disadvantages. There's duplication, because every time I link something, I have a new copy that's linked into the process. Okay. And if there's a minor bug fix, I have to rebuild things to include it. I have to rerun the static linker. Shared libraries are another solution. We talked about these a little bit at the beginning of class. They allow runtime linking, the inclusion of chunks of code at runtime when it's needed, a late binding. And the advantage of the late binding is that, A, if there's a fix, it can get found because it's bound in late, and B, we can all share these objects because I can have one copy of a shared library in memory, and that same copy can get bound to multiple executables because the code is read-only anyway. Okay. So dynamic linking can occur when an executor is first loaded. It's certainly the case that we can load a process and immediately link things in. In fact, we can preload libraries if we want to. Just because it's dynamically linked doesn't mean it has to be linked just in time. It can also occur as the program is running. There's a library called DLOpen that does this. Okay. So we have LD that runs at compile time to generate a process image. The process image is loaded by an exec, and then at runtime, the runtime linker called ld.so is run and does the final link. Okay. In the context of normal processes, we as programmers do not worry or think about dynamic linking. And I want to make this very clear before we dive into the next bit of slides. In the normal process, dynamic linking is handled automatically for us. What happens is, at compile time, a small, thin stub is linked in instead of the actual code. Okay? This satisfies the requirement that all symbols be resolved at compile time. Now there are no dangling symbols. Some symbols have been linked to the actual code. Some symbols have been linked to the stub. Does that make sense? So at the end of static linking, all symbols are resolved one way or another. If they can't be resolved, then the linker fails and we get an error. At runtime, for these certain things, these certain functions that were dynamically linked, right? They were linked to the stub which runs, and the stub causes the real function to be linked in, and then the real function to be called. Okay, it does this through two data structures. One called the global offset table, and the other called the procedure linkage table. Basically, it's indirection. The call is indirect via pointer, and the first time this pointer is pointing at the dynamic linker, which links the function and then calls it. The second time, this function is now pointing at the real function because the pointer's been updated. So the second time, the actual function is called. Do you see that? Initially, this data structure holds a pointer to the linker. So we try to call printf. The linker instead gets called, recognizes that we're trying to call printf, links in printf, updates this variable. We return, it tries again, and now it succeeds. And now every future call through that variable is actually going to call the right function. It's actually one step worse than that. The first time we call a dynamically linked function, it calls the dynamic linker function, which is dynamically linked. And so it calls basically a bootstrap function to link the dynamic linker. Update the variable, fall back. Now the dynamic linker is called. Now it realizes it's trying to call printf. It links in printf, updates the table, falls back, and now printf is called. Does that make sense? That's the way that's normally handled at runtime. We as programmers don't need to think about it. The static linker resolves all of those symbols against stub code. Then at runtime, that stub code runs, as I described, using indirection via the PLT and GOT to actually call the functions. Now, is that a little slower? Yes. Right? At runtime, there's some indirection, and sometimes we're calling linker functions. Is that a lot slower? No. The indirection probably costs us this much against the size of that function. It's not significant. Not usually, at least. What advantages does it give us? All the advantages we talked about for dynamic linking, right? That's how we implement that. Now, what we're talking about here is how you as programmers can gain control of dynamic linking at runtime. It's not the normal mechanism. It's just a mechanism that you can use. Okay? You can call dlopen and give it the name of a library you want to open. Okay? As well as a flag. In this case, the flag says we want to link in a lazy way. Okay? Now, we can use dlsim to search this library that we opened and for which we got a handle. Search that library for a function, in this case called advec. It returns a function pointer to which we assign to a variable oddly called advec. Now we can use that function pointer just like a function. Because ultimately a function is just the address of a function, right? So now we have the address of a function. So now we can call advec as if it were any other function. We have manually dynamically linked it. Does that make sense? And then we're done. We can call dlclose, giving it back that handle, the handle that originated with that open, that dlopen. And now we're done. Make sense? Okay. Library interpositioning. In other words, replacing function calls from a library with other function calls from a library. Yes?
If you want to use a function, if you want to use a function more than once, like in separate functions, for example, would you be better off importing rather than dynamically multiple times?
Okay, so you're talking about, when you say dynamic linking, do you mean dlopen?
Yeah, if you do dlopen in one function, like say you do that in main, then you have like some other function which calls it for the same file and you get the same function, would you just be better off importing it?
Look, I mean, you might be better off linking against it manually, right? It's not clear to me why you'd be doing a dlopen in a general case anyway. So you have to talk about the specific case. But if you wanted to use dlopen and needed to use that variable in multiple functions, maybe then, like other functions, it becomes a global variable. right? Because most of your functions are global variables, as it turns out, right? It's not, it wouldn't be unusual to have a global variable reference a dynamically linked function. Does that address your question? You sure? Okay. So library interpositioning is basically this idea of replacing one library call with another library call. We can do it at compile time, we can do it at link time, we can do it at runtime. Let's take a look at how. Or let's take a look at why. We might want to interposition calls to disable things. We don't want you to use networking, so we're going to replace networking calls. We may want to monitor and profile. We may want to find out how many times a function is called. So we may want to replace the function with some wrapper function, and then have that wrapper function call the function itself. Okay. We may want to do things like get address traces, like replace malloc with a function that tells us what addresses are being returned. So we can then look to see later on what frees are happening. Let's say our goal is to trace this. One easy way of tracing this is to write our own library that has our own version of malloc and our own version of free. I'll call it my malloc and my free. And my malloc, for example, keeps track of the address returned by malloc. In this case, it prints it out. Okay? And it calls the real malloc. Okay? My free literally just calls free. Now, notice over here, I have a pound define replacing malloc with my malloc, and replacing free with my free. So here's the idea. If I have main.c and some library.c, and now I have my memory, my tracing library. My tracing library has my malloc and my free, uses malloc and free. The rest of them have no reason at all to call the real malloc and the real free. So I pound define in those functions malloc to get replaced with my malloc, and free to get replaced with my free. So now the preprocessor goes through those and replaces them. So where the programmer is trying to call malloc, it instead calls my malloc. My malloc is still free to call malloc because it's in a different file and hasn't had that preprocessor substitution made. Do you see that? Okay. So that's one way of handling it. Another way of handling it is to get some help to do exactly this, but using some linker options. The linker option here is called wrap. Underscore dash dash wrap comma malloc. Dash dash wrap comma free. Okay? That's asking for the same for the linker to do the same thing for us. And so now we write a function called wrap malloc, and we write a function called wrap free. Okay? And the linker is going to automatically wrap my malloc with wrap malloc and free with wrap free. Okay? Then as to what happens to the real malloc and real free, they get called underscore underscore real underscore malloc and underscore underscore real underscore free. So our wrapper functions use the real versions, and at link time, the linker replaces the calls to the real versions with calls to our wrapper functions. And these names are formulaic. It's always underscore underscore real underscore blah. It's always, underscore underscore wrap underscore blah. Does that make sense? Yeah.
So, am I right in assuming that it's sort of bad practice to name your own functions in that formula? So
yeah, it's bad practice to name your own functions anything that begins with underscores, because those are generally reserved for the linker.
Got it.
You can use underscores in other places, just not the beginning. Okay. And now we see how that works. All right. You can also do it at runtime using the functions that manipulate the dynamically linked library, right? So what's going on here? Okay. Well, we see it's calling dlsim. Okay. All right. Boom. Malloc. And now we're getting a pointer to malloc. Okay. Beautiful. So now I have something called malloc p that's a pointer to this malloc. Okay. Now I have pointer equals malloc p of size. Fine. So you can see that I just loaded a function called malloc p. Okay. Now, what to say about that. This is what this is. Now, how do we get to where this is useful? If you look at the very top, you see this LD underscore preload. Okay? That's an environment variable. Okay? That's defined outside of your process in the environment in which it runs. Most commonly, you have a shell. Your shell has an environment, and then when you start a process, it runs in this environment. And so you can use an LD preload to load a library before your process runs. You can set this variable and say, LD preload this library. And then when the linker runs, it says, when the loader runs, it says, the environment tells me I should load this first. So now, instead of linking to libc or libmath or whatever, right, it's going to preload your library, which is going to bind to all of those symbols. So now, when the real libraries run, they won't. Or get linked, they won't. Okay? So that's how preload works. Okay? Okay. Boom. The LD preload environment variable tells the dynamic linker to resolve unresolved symbols by looking in whatever it's told, right? And so here we see an LD preload that's preloading libdl and my malloc library, right? And so now it's going to preload my malloc library. All right? Now the question is, how do I make my malloc library such that it can be used as a shared object? Because by default, we said it gets compiled to a .o, not a .so. And the answer is you can look right here and see this, right? The magic two flags here are minus shared and minus fpic. Okay? Shared says it should be made such that it can be a shareable library, and fpic says position independent code, meaning it can get moved around. So now it's shareable, and it can get moved around as it needs to be. Okay? Meaning that in one process it can be linked in this location, and in another process it can be linked in this location at the same time. Okay? So the two magic things on the slide, right, are compiling with minus shared and minus fpic, such that we can build something that can be used as a shared library, and setting the preload variable to cause that to be preloaded before other symbols are resolved, so symbols resolve against it. And now our versions of malloc and free are being used to satisfy the dynamically linked malloc and free instead of those from libc. Compile time, link time, and run time. Okay? Compile time, we do it by pound defines, substitutions in our code. Link time, we can use the linker flags, right, to wrap. And at runtime, right, we can use things like preloading, right, or things like DL open to satisfy the problem. Any questions there? How many weeks away is the mid-semester exam?
2.
Very good. You had your hand up.
No, I was just saying 2.
2. Oh, 2? Yep, 2 weeks. How do you prepare for the midterm exam?
Practice exam.
Write them over and over again.
Do what over and over again?
Print out a bunch of exams, do one, do another, repeat ad nauseum, or ad infinitum, whichever comes first.
So sort of, right? Remember my suggestion, right? That you go through and you digest a whole bunch of the old exams, making piles, right? Where you pile all the integer questions and all the floating point questions and all the, the assembly struct questions and assembly array questions and stack questions and cache questions, right? Because the exams are formulaic. There are 8 questions or so on all of them. They're all the same types of questions. It's been the same way since 1998. Okay? So if you haven't already, take a bunch of them and stack them in piles. And my general suggestion is after we finish a lecture, do the questions out of the corresponding pile. That way you actually learn the stuff from that lecture, right? And do it until they get boring, because that means you're getting them correct and doing it without stress, right? And then when you roll around to the mid-semester exam, take a couple of whole mid-semester exams, right? Like the 2 most recent that you didn't shred. Or if you've actually gone through all of them, just take one question from each pile and make your own mid-semester exam. What do you think we do? I mean, really, right? And then take a couple of them just so you get a sense of the timing. Okay? And then if you have any weaknesses, go back and do more questions from those piles. Then take another exam for a sense of the timing. If you have a weakness, dive in. If you run out of questions, take one out of each pile and call it an exam. Okay? That's literally how the exam is made. Every semester, we put like 2 new questions into our pool. And so our pools grow. But you literally get 1 question out of each pool. There's a question 1 pool, question 2 pool, question 3 pool, question 4, and so on. And you get 1 question out of each. Okay? That's how your midterm exam gets generated by the system. If you do more old problems, right, it actually helps you in 2 ways. A, you learn more, and B, there's a good chance you'll see one of those problems on your actual mid-semester exam. Because we started out doing this I think 2 or 3 years ago with completely old questions. And since then, we haven't taken them out, right? We just add new questions to make the pools bigger. So originally, right, you were guaranteed to get an old question on your exam, right? Now, I don't know what it is, maybe 50-50. Maybe it's 40% likely you'll get an old question. But it is what it is. Yeah?
What year did the 64-bit questions start?
The 2 years before your textbook. Yeah, because we did them with a supplement when that came out. Yeah?
What happens like if the system just gives you the hardest question in every pool?
What happens if the system gives you a hardest question every pool? So 2 things, right? We've been working over time to eliminate the magical hardest question, right? Because if we see a question that a whole bunch of people are missing, we go back and ask ourselves why. And then we try to revise the scoring on that question or the question to make it more normal. So the chances of that happening to you now are much lower than that happening to the people the first time we did this. Because anytime we've seen that, and we do build a spreadsheet of that, we fixed it. Okay? The next thing we do is we actually do look at the end to see if we're screwing anybody. And it's never been the case that we have, because some people have gotten hard questions, but they've also gotten easy questions. So when we've computed the average unfairness of the exam, it's actually been exceptionally low. And when we've computed the maximum unfairness of the exam across the class, it's actually been the person who got the worst exam, right, it's actually not been that bad. And then we did that across both the mid-semester and the final, the unfairness basically went away. But we do look at the spreadsheets, and if we find that we're actually damaging somebody, we'll make an adjustment because we have the data. But it hasn't been necessary yet. Now, if something happens, we'll have to deal with that. The biggest problem we have in the pool right now are that questions have different levels of resolution, meaning that some questions, it may be the case the question's worth 15 points and they have 5 parts. So each part's worth 3 points. On another question, it may be worth 15 points and there are 2 parts. And now each part is worth 7 points. And on another version of the question, there might be a nasty cascade problem where if you miss the first part, you blow everything. And so in those cases, the averages might land the same, right? But the distribution is not. And those are the questions that we're actually trying to identify and shake out of the pool at this point. So I don't want to claim the exam is perfect. It is not. What I will tell you is that no exam is perfect. In the past, right, we had those same questions, although they may have appeared there may have been a difference between the afternoon section and the evening section, right, because we had 2 different exams, or between fall and spring, or, right? So now we're able to see all of that at once and try to fix that. And so things are actually getting better, not worse, but still not perfect. My hope is that eventually what happens is we get to the point where the pool is big enough that we introduce all new questions into an experimental pool. We collect the data on them to verify in advance that they're fair, and then eventually roll them into the real pool. But right now we've had too strong a desire to dilute the old questions that are still in the pool with new ones. Because to dilute the ones that are already published. And so we've been taking our best guess, practicing them, right, giving them to some alums and some TAs and whatever, and then introducing them directly into the pool. And we've largely been very good, but the stack question, to be honest, is one that's given us some trouble, right? Small errors in the stack question can cause large errors in grade. We've been trying to work that out, but it's tough. Because if you get your addresses wrong, we don't necessarily know what you're thinking, and the computer certainly doesn't. And there's one of the array questions in particular that also has been a little rough, because it's been mostly all or nothing. We've been working on that too. But what I can tell you is we're actively thinking about these things and doing our best to make the exam as fair as possible. I'm convinced that it's an extremely fair exam. I'm convinced that there was more variance in grading by humans in the past than there is now in question difficulty. That is to say, if somehow we were to measure your true knowledge and gave you a paper score, I think that the variation of your true knowledge when that paper was graded by one of a dozen TAs would be greater than the variation right now, depending upon which form of that exam you get, graded by the auto-grading machine. People make mistakes when grading, right, that might or might not get detected. One TA might understand what you were thinking and fix that. Another TA might not, right? And so this system is actually, I think, much fairer. Does that address your concern?
Yeah.
Okay. Yeah.
In the past, for the averages on the midterm to like the average of the class, like final grade?
For the mid-semester exam or for the midterm course grade?
Yeah, without work yet.
Which one do you want?
For the mid-semester exam versus mid-semester grade.
So the mid-semester exam has been sitting, I believe, in the low 80s, which is higher than we would actually like it, but we haven't done anything about that. The course is set up and has been for many years to have an exam average in the low 70s, because project averages tend to be high. And so if we have an exam average in the low 70s and the high project scores we see a course average in the low 80s. And that's what we like because that provides a meaningful distinction. When we went to the online exam, because we made time infinite, right? It's not actually infinite, but it's like 5 hours or something, right? We took off all the time pressure. What happened is some people who were just being defeated by time, right, their scores went up. And the effect is that we actually have a much better measure of understanding, we think, at least of measuring what we'd like to measure. We never intended to measure time. It just happened. So the scores went up, and we haven't adjusted the course for that. Over time, I think we might, but that hasn't happened yet. Instead, course averages just have gone up. It always was to be done in about 80 minutes. We haven't added questions. We haven't changed questions. We haven't changed the complexity of questions. Like I said, a bunch of the questions are still the old questions. And we've really held that line very strongly. We believe that the exam can be done in 80 minutes. We believe that as much today as we did, in 1998 or 1999, whenever we went to this exam format. Having said that, right, for those who were, who took those exams in those days, there was a lot of time pressure. You basically got to race through the exam once and didn't get to go back through anything again. That's not the desirable way to take an exam. And so although we believe that the exam can be fairly taken in 80 minutes, we believe a prudent student would probably take a little more than 80 minutes to take the exam, right? To do things once and then go back and check things that are not, and double check things where they had doubts, right? And so it doesn't surprise us that the average student is taking, I have to look back at like 140 minutes for the exam. Something like that. I have to look back to give you an actual number, but that's not far from the actual number. So we'll say the average student on an exam that's designed to be, 80 minutes is probably taking, just under an hour and a half is probably taking just over 2 hours. And again, I have the actual data. I just didn't look at it before class. So I'm guessing a little bit, and that's sort of perfectly okay with us. We don't find that to be surprising or inconsistent. That makes sense. Now, occasionally somebody camps out with their exam for 5 hours, and I have to tell you, we all wonder what you're thinking. Like, what is that person doing? Are they still there? Their eyes open? Should we go wake them up? No, they looked at me when I walked by. Really? Do they have a book? Are they reading? Like, no, there's a Bible. They're praying. Like, whatever, right? Forgot how that went. It was a conversation with TAs. Like, did you look at that person? Are they awake? Like, maybe we should wake them up or something. Like, no, they've been there for 4 hours and they're awake. I'm like, they don't seem to be typing. No. I think they have a book out. I think they're reading. Oh, they're not allowed to have books out. They're only allowed to have notes. Well, I think it's okay. Well, why is that? It's the Bible. There is no exception for the Bible, by the way, but that was the joke, as we're trying to figure out what the student was doing there for hours. And so look, if you need the time, take it. Because what I'll tell you is, right, if you spend 5 hours for your exam and you get an A instead of a B in the course, is that worth it?
Yes.
Yeah. Like, like, you know, we don't intend for that to be the case, but if we're surprised, we're surprised. I can tell you when I do set the program that does the exam scheduling and lets you pick your slot, I don't assume that everybody's going to take 5 hours for the exam. If everybody did that, there wouldn't be enough seats. You know, I assume something, you know, much more conservative than that. But that's not your problem, right? You should take as much time on that exam as you believe you productively need. There's no reason to hold it close to you for longer than when you're done, but there's no reason to rush through it. Take your time, deliberately, go through the exam. Answer the questions well. Check your work as you go. If you had doubts about something, go back to it. Right? If something's blowing your mind and it's confusing you, go to another question. Come back to it, read it again. Maybe your brain will reset and it'll make more sense. Right? The time is yours to use. The goal is to reduce your stress level. That's the only reason we do the exam. The online exam does not save us 1 minute of TA time. Not 1 minute, okay? Because guess who's proctoring the exam for 4 days? The TAs, right? They spend as much time proctoring as they used to spend grading. It saves the course staff not 1 minute of time. The only reason for it is that we believe it improves the quality of education by allowing you to relax and take the exam under less pressure and more friendly circumstances. By letting you pick a slightly different day if your mid-semester week is busy, right? By giving you a huge amount of time so you don't go into it feeling rushed, right? We figure by giving you more time, you'll actually finish the exam earlier because you won't be in that rush frenzy, right? You'll actually be relaxed in taking it, working much more efficiently. So the goal of the system 100% is improving the quality of education you get, improving the quality of your experience. Doesn't save us a dime, doesn't make us more scalable, doesn't do anything else. Yeah?
So it's just like Monday through Thursday then?
The plan right now is Monday through Thursday. We're still massaging the lab reservations. As you can imagine, for 500 people to do this, it is quite a footprint on our public computer labs. It is what it is. But we're trying to do that in as user-friendly a way as we can for others. Any other questions? Yes?
When will signups be starting?
Signups will be starting probably early next week, or maybe late next week. The reason that signups happen late is that we have such a huge footprint. I don't want to lock it down early because that prevents other people who need the labs for their own exams from getting them. And I feel like we, as the elephant, need to work around them rather than them working around us. And that's the reason, you know, that we lock the reservations down late. You know, many of you guys know I'm the director of educational computing. I'm the one who approves all these reservations. And so I could, by fiat, just do it. And we could have done this by fiat, you know, in August. But that's not the correct or fair or friendly or community-oriented thing to do. And so, you know, it might be the case that if we have to have some holes cut through when the exams can be, because somebody else needs to give one, somebody else needs a review set, whatever it is, in which case that's what we'll do. Any other questions? Have a great day, everybody.